Good evening, everyone. And I extend my heartfelt thanks to Professor Mayank and Professor Pavan Goel for giving me this opportunity to interact with you. I'm sure you have been treated with a fantastic lecture by Professor Ashutosh on several parameter efficient fine-tuning techniques. So in this hands-on session, I will be mainly looking at two recent techniques. One, obviously you have heard of it by now, which is LoRa, low rank adaptation, and the second one will be QLoRa. So let us start off with that. And before going into the actual LoRa implementation or how you can use Hugging Face libraries, I will also show you how you can actually code up LoRa from scratch, from absolutely nothing. I mean, just using the Torch library. Okay, so yeah, so let's move ahead. So what are the problems with fine tuning? And yeah, I mean, if you have any questions in between, please feel free to ask me. I will try my best to cover them. Okay, so by now you already have a fair bit of understanding of what are the main issues with fine tuning, but just I would reiterate these 3 points. So first of all is that the training the full network is computationally expensive for the average user when dealing with LLMs like GPT, which by now we all know. Then if you want to save the checkpoints, the model checkpoints, then storage requirements for those checkpoints are also very expensive, because at every checkpoint we are saving the entire model plus the optimizer states on the disk. So there is a huge requirement of the huge storage requirement as well. And then let us say if you have multiple tasks, for example, you have a pre-trained model like GPT or something, and you want to build your own custom application. One maybe for writing some JavaScript queries, and one maybe for writing some SQL queries. Now both are related to queries, but since the languages are different, one is SQL, one is JavaScript, you will have to fine tune the model or prepare your model in two different ways. So if we are going for full fine tuning, then you will have to, first of all, you will have to train one complete model for each different kind of a task, and then you will have to save it as well. So these things are good as far as the academic setup is concerned, but when you go to industry level production, these things have a bottleneck, because you cannot save multiple different models for multiple different things. There needs to be an optimized way of it. So that's why we look into these parameter efficient fine tuning techniques. So the crux of LoRa, by now you have already learned about it. So the crux is this: how or why LoRa at all works. Okay, so in the following few cells, I will try to explain that. So this is like simply we are importing some basic libraries, Torch and NumPy, and we are setting the manual seed to 0. This is just for ensuring that every time you run the same thing, the same results are appearing. So now let us say that we are creating a matrix. Let us say this is our weight matrix, okay, which has the input dimension D and the output dimension K. So D cross K matrix, okay, and let us say both are 10 and 10. Now what we are trying to do is we are artificially creating a matrix with a rank of 2. So instead of initializing a 10 cross 10 matrix, what we are doing is we are first initializing a 2 cross 10 matrix, okay, a 10 cross 2 matrix here with a rank 2, and multiplying that with a 2 cross 10 matrix, okay. So we are creating the weight matrix in such a way that its intrinsic dimension is very less with respect to its original dimensions, okay. And by intrinsic dimension here I mean the rank here in this matrix is 2. So we are creating this artificially. So fine. So ultimately we get our weight matrix, and you can see that these are the tensors. Okay, it's a 10 cross 10 matrix. Fine. So let us go ahead. Now, if we simply print the rank of this matrix, then you can reconfirm that the rank of this matrix is 2. So although there are 10 different columns, but by now you already would have understood that there are only 2 columns, let us say, which are linearly independent of each other, and the other columns can be linearly combined with these two columns, and therefore these are redundant. So the actual information is mainly saved within the within two columns only rather than the 10 columns. So that's why the rank is 2 here. Okay, and why the rank is 2 here? Because we artificially created in such a way that the rank is, we are creating this matrix in a way such that the rank is 2, and that's what we basically verify here. Fair enough. So now what we are trying to do is we will try to decompose this weight matrix. That is what we are basically, that is what the crux of LoRa is, right? So we will try to decompose this weight matrix into two smaller matrices. So first, let us say that if we apply this command torch.svd, then this will give you three different matrices, U, S, and V, three different matrices, and this is the calculation. So U cross S cross V transpose will give you back W. Singular value decomposition is performed on the weight matrix, and you get three different matrices. Now, the refactorization that we are trying to implement here with a rank of R. So let us say we are only considering the first R columns, right? The first R columns of these metrics. So from U, we are only considering the first R columns. Similarly, for V, we are only considering the first R columns, and then we make it a transpose. And the middle one, it is basically going to be a dialog, only the diagonal values of the S matrix with only the first, again, only the first two columns considered here. Where by two, I here mean the rank. Okay, so now let us create the B and the A matrices, which you have learned in LoRa, right? So if we create this matrix, then B is basically U multiplied by the diagonal SR, and A is VR. In this way, we create the two matrices. Now the multiplication of these should give us back the original matrix W. If it gives, then this proves that, okay, if there is a weight matrix whose intrinsic dimension is lower than its actual original dimensions, then it can be broken down into two different matrices B and A in such a way that when we multiply B cross A, then it captures all of the information, okay, that W originally contains. So that is what we try to achieve using LoRa. Okay, so fine. So we are just printing the shapes here. So B and A, you can see it's 10 cross 2 and 2 cross 10. That's fine. Okay, so now we are simply initializing X, which is our input, okay, randomly, and we initialize some bias randomly. So now this is our original calculation, like W into X plus bias, which is the full fine tuning part, right? And then we also calculate Y prime, which is B multiplied by A. This is a LoRa computation, a low rank computation. B multiplied by A into X. So B multiplied by A will give you the same dimension as W. Then you multiply with the input and then add the bias. So now if we print this, then you will see that these are, I think, exactly the same here, because there is a toy example. But the thing is proved that if there is a weight matrix with a lower dimension, you break it down into two lower dimension matrices, multiply it, and you capture all the information, the important information that is there in W. Okay, and finally, I mean, the total number of parameters in W obviously is 100, 10 cross 10, but in B and A, it's basically 10 into 2 plus 2 into 10. So basically 40, right? So we obtain a reduction of the parameters. Now, as obviously this is not a great reduction of parameters, this is just a toy example, but as the weight matrix, as the dimension of the weight matrix increases, you will be better able to appreciate how much improvement or how much space improvement we have with LoRa. Okay, so now let us try to implement LoRa using PyTorch. Okay, fine. So these are some of the basic imports. We need some data sets, some transforms, matplotlib to
Sir, I
make
have a
some
question.
Yeah.
Sir, you break down the W into 10 into 2, 2 into 10.
Yeah.
So 2 is the rank of matrix?
Yes, rank of the W matrix.
Okay, thank you, sir.
Yeah. So that is how we basically created the matrix in the first place. We set up a rank of 2. This is W rank is 2. And then we create the two matrix, D cross W rank and W rank cross K. Okay. By here, D and K both have the same value, but they could be very well different values as well. Okay. And then we create the original weight matrix. This is how we are creating the weight matrix, just to prove that, okay, if the intrinsic dimension is 2, the rank of the weight matrix is 2, but we are creating a 10 cross 10 matrix. Now can we divide it into two different matrices? And that's what we showed here, that yes, this can be divided into two different matrices, B and A, which are of lower rank. So one is 10 cross 2 only, not 10 cross 10. Another is 2 cross 10. So you multiply 10 cross 2 multiplied by 2 cross 10. Okay, the columns in the first one matches with the rows in the second one, so multiplication can happen, and you get back 10 cross 10 matrix. That is what we try to achieve.
Okay, sir.
Okay, fine. Okay, so fine. These are some basic imports. These are required. You make the torch model deterministic by setting the manual seed. You can set it to any other value as well. Okay, now we are loading the MNIST dataset. Now, MNIST is basically a very famous dataset from several ages back now, which is basically consists of digit classification dataset, right? Now you will be shown images of digits and you will have to classify them as what digit they are. Okay, so you load the MNIST dataset here. You prepare a train loader. These are simply, I mean, the simple steps that you would need for any, model training. This is the test set and the test loader. All that is done, and then you define your device. Okay, and all this will download your dataset and prepare it. Now I am creating an artificial neural network, which is very much expensive. Deliberately I'm creating a neural network just to show that we can achieve similar performances using LoRa with much less parameters being fine-tuned. Okay, so this MLP, multi-layer perceptron, this consists of 3 different layers. All right. So the first is 28 cross 28. So these are the features into hidden size 1. Hidden size 1 by here, we can see is 1000. It's pretty high. The hidden size 2 is 2000. So this is a huge model, right? And finally, from hidden size 2, there are 10 different digits. So the final output layer will be 10. And there is a ReLU. Fine. So the forward block is simple. You pass it through, I mean, you take the image features, you pass it through the first layer, the second layer, and the third layer, you get the output. Okay. Now, here you are creating this expensive net. I've just named it like that. Okay. Now, this is your training block. So we are training the network only for one epoch to simulate a complete, general pre-training on the data. So let us say that we are just, you have this block to train your model for just a single epoch. You can obviously change the number of epochs, as many as you want, and you can get the training done. So fine. So once your training is done, then what we are doing here is we are keeping a copy of the original weights, just cloning them. So later we can prove that fine tuning with LoRa doesn't alter the original weights. By now you would have already known that LoRa does not, change the original weight matrices, the original weights of the model. The original weights are frozen basically. Okay, LoRa uh, is adding these two additional metrics. You can call it adapter or these additional two different things, B and A, which it will be fine tuning. Fine. So let us simply clone here. Original weights, we are simply cloning the original weights of the model, not doing anything fancy here. Okay. Now let us check the performance of the pre-trained network. By pre-training means, I mean, this network is obviously not trained. I mean, there's a very simple network. So we train the model for one epoch, and we are just calling this our pre-trained model. Later on, when we will be dealing with large language models which are pre-trained, so let us say this will be our starting point, this pre-trained model. Okay, we are doing it just for one epoch to simulate the scenario. Fine. So now let us check the performance of the pre-trained network. And I just ran it, and as you can see that on the digit 9, it is making the most number of errors. Okay, wrong counts for the digit 9 is 87. So now our target is that, okay, I mean, now we will keep the model intact, and we will only fine tune for the digit 9. We will not fine tune for the remaining digits. That is our target. So this simulates the scenario that, let us say your large language model is pre-trained on a lot of different tasks. Now you have a specific end task for which you want to fine tune the model. This is to simulate this scenario. Okay, you have different things, but you only want to fine tune the model for improving the performance on digit 9. That is your end task. That is your goal. Okay, now this will be doing using LoRa. Fine. So here, let us now visualize how many parameters are there in the original network before introducing the LoRa matrices. So that's fine. So layer 1 is 10,000 cross 784. Why 784? 28 cross 28. These were the image features, right? And the bias is fine. You can see the weights here. So 1000 cross 784, 2000, 1000, 10, 2000, right? These are our 3 layers of the original model. Okay. So now let us define our LoRa module, LoRa parameterization. So there will be one features in, which is our D. There will be one features out, which is our K, right? Here we are defining the rank and the alpha. I will come to alpha later. So first we will be defining LoRa A, the A parameter, right? And this is basically everything is with zeros initially, okay? And this is rank. For example, here I'm using a rank of 1. So this will be 1 cross features out, which is K, right? So the multiplication goes like b into k, sorry, b cross a, right? In order to get back our original W matrix. So the A should have features out similar to the features out of W. So that's why it has been initialized with 1 cross features out, and B has been initialized with D cross 1, right? And the multiplication will go from B to A. So you will get back features in, comma, features out, your ultimate weight matrix. Fine. And then in the paper, they say that in the LoRa paper, they say that we use a random Gaussian initialization for A and 0 for B. So B is anyway initialized to 0, and we simply make a random Gaussian initialization for the A matrix. Okay. Now this is a scale parameter. Okay. So when your delta wx, I mean this delta w, when you're, I mean the gradients, you are using, you are not touching your original weight matrices, right? Using B and A, what you are calculating is basically you are calculating the gradients. You are calculating the updates that you would like to make into the W matrix. So you are only calculating the gradients. Now, if you want to scale these gradients by some value, then you can play around with this alpha, variable, alpha hyperparameter. Okay. Now there's a scaling parameter, as simple as that. Now in the paper they have mentioned that okay, you set it to a set your alpha to the first R that we try, and then you do not tune it. Is as good as tuning the learning rate. All right. So you can set it to the same value, or in many of the implementations you will see that alpha is usually set to 16 or 32. I mean, when you go to large language models, for example, GPT-2, GPT, Llama 2, and all those things, then rank is usually kept as 8 or 16, and alpha is usually kept as 32, 16, like that. So usually a scaling factor of 2 or 4. That is the norm. But again, these are hyperparameters. You can always play around and you can see, like on your dataset, what performs best. Here I have simply kept it as 1. Okay. And then there is a value called this argument called enabled. If you set it to true, okay, then the forward block, this will be helpful. If you set it to true, then you will be returning the original weights, that you will be returning the updated weights. So original weights plus the multiplication B cross A, right? This is just a view, and then you scale all the gradients. So B cross A is giving you the gradients, original gradients, and then you scale the parameters using the scale value that you have set here. Okay. And if you set the enabled equal to false, then you return the original weights. These will become more clear as we go below. Okay. So this is just the LoRa parameterization class that you define. This is implementing LoRa from scratch. So that's why these many details, I'm discussing these many details. Later on, you won't need it, but this is good for you to probably understand. Okay. Then there is this function called linear layer parameterization. So how does LoRa ensure that when you are applying LoRa, how does the weight matrix, the original weight matrix gets replaced by the LoRa calculated weight matrix? Okay, you can read more about parameterizations here. I mean, there are some PyTorch tutorials that you can refer to, but here you can simply look at these 3 lines. So when this thing is set to enabled equal to true, then these parameterizations will take place. So in the linear layer 1, the weight matrix, the original weight matrix, if there is a parameter called weight, which is the original weight matrix, that will be replaced by your linear layer parameterization of linear layer 1. Okay. And where is this linear layer parameterization coming from? This is basically this function which will return you this LoRa parameterization. And what is LoRa parameterization? This thing. If you set it enabled equal to true, then you will return the original plus the calculated weights. So basically the updated weights, right? So this object is being returned. So the weight will be replaced by the actual linear layer parameterized weights. Similarly, for linear layer 2, for linear layer 3, you simply do this parameterization. These are called register your parameterization. Okay, this is how LoRa is implemented internally. Okay, and then you can simply define another function for all the layers. I mean, you are just putting weight of 0 dot enabled equal to enabled so that LoRa actually works, right? Okay, so now let us see the number of parameters which are added by LoRa, right? So these were our original parameters, and then you can see with a rank of 1, LoRa A and LoRa B have been added. So 1 cross 784 and 1000 cross 1, these have been added. These are added for linear layer 2. These one, LoRa A and LoRa B for linear layer 2. Similarly, for linear layer 3, these are our LoRa A and LoRa B. So for every layer, you are adding the additional B and A matrices, right? And you can also, set for which of the matrices basically you want LoRa to calculate the weight updates. That also you can set. It is not necessary that you calculate LoRa for every layer or for every weight matrix. Okay, usually when we will look into large language models and some implementations on that, then you can set up. By now you obviously would have understood the basics of the transformer architecture. So there are 3 different attention matrices, right? There are 3 different matrices which are used to calculate the attention matrix Q, K, and V. So you can always set like for which matrix you want to apply LoRa, and for which you do not want to apply anything, just keep the weights frozen. So here I'm just applying LoRa to every layer. So that's why you can see these are the weight additions. Okay, so total number of parameters original was this. With LoRa is this. Obviously, some number of parameters are added, but this is just 0.24% increment. So not a big headache, because at the end of the day, all these parameters like 2 lakh, this 2,807,000, all these will be simply frozen. Only 6,794, these will be updated, right? Okay. So now exactly that we are doing here. So if the name LoRa is not in your parameter, names, then you simply put param dot requires grad equal to false. So basically, we are not going to update the other parameters. We are only going to update the LoRa parameters. That's what it is doing. Okay, and then we are basically training this. We are setting all these things. We are simply setting the target to 9. That means we are only bothered with the digit 9. If the weights should not be updated for any other targets. We are only concerned about 9, that digit 9, and we want to improve. Hopefully the performance on the digit 9 will improve after we train our model. Okay, and these, you can see that these lines are basically freezing the non-LoRa parameters, the bias and the weight original parameters and all that, because see, the original weight parameters are frozen. Okay, the LoRa matrices are not frozen. LoRa matrices will be updated. Okay, so fine. These are some asset statements we had. So earlier I had shown you. Yeah, there was some question. Okay, I will move on. So earlier in one of the cells above, I had shown you like we are cloning the original weights, right? Just to ensure that LoRa is not updating any of the original weights. So these are those asset statements. If these asset statements fail, then obviously something creepy must have happened. LoRa must have updated something. But all these asset statements basically pass, so you can also verify, and which proves that LoRa is not changing any of the original weight parameters, right? Okay, and then we are simply setting the enabled argument to true, so that LoRa can run. And after LoRa runs, then we are asserting what? We are asserting whether the linear 1 weight and the parameterizations dot original weight plus the LoRa B into LoRa A, whether this is equivalent to the new weights. So this is just one more asset statement just to check that whether we are getting the updated weights or we are getting back the original weights. So I had shown you above that if you set this enabled equal to true, you will receive the updated weights. If you set this enabled equal to false, you will receive the original weights. So these are just 2 asset statements just for sanity checking. Okay, nothing else. Okay, now we will you know, test the model which has been trained using LoRa. So we enable disable LoRa, we set enabled equal to true. So you know, this function will work, and the model will be trained using LoRa. And once the model is there, then we test it. So when we test it, we see that the wrong counts for the digit 9 obviously has reduced, but I mean, the other things have gone haywire. So the performance on the other digits has dropped down. But this is just a toy example to prove that LoRa actually works. And if you are only bothered about your end task, then obviously you don't care about what other tasks are failing or on which other tasks your model is not performing good. Because at the end of the day, you only are bothered about your end task. So if the performance on your end task is improving, that is what we care about, right? So that is what supervised fine tuning is all about. So that is what we are achieving using LoRa. Okay, so this was implementing LoRa from scratch, and we are applying LoRa to a very simple classification network, right? Usually nowadays you will be talking more about large language models and whatnot, which are generative architectures. But this is a very simple example just to show that LoRa can be applied to any kind of neural networks. You just have to decide on which weight matrices you want to apply LoRa, and accordingly you set all these you know, classes so that you can have your desired output. Okay, so fine. And if just to ensure again one more round of sanity checking, just you know, set this enabled equal to false. The moment you set enabled equal to false, now you can see that the original values you can get back. So originally, if I go above and I show you that originally there were 87 mistakes, right? Where is it? Yeah, there were 87 mistakes on digit 9. So if you do not apply LoRa, that means you're not applying any fine tuning, just with the original weights, right? Then you get back the original results as well. So all the magic that LoRa was basically playing, that is gone again. So this is just you know, a toggle. I mean, just a control parameter, just for your own checking, like whether LoRa is working properly or not. Okay. So yeah, I mean, that completes the implementation of LoRa from scratch and applying it to a classification network and see whether the results are improving or not on a specific end task. If you have any questions here, then I will probably stop for a minute.
Sir, am I audible?
Yeah, you're audible. Please.
Okay. Sir, if I'm trying to create a language model which is going to perform multiple tasks,
Hmm.
does LoRa perform very low? Because should we not opt for a LoRa pre-training or a LoRa fine-tuning technique? Because before the error was around 386 classifications gone wrong. But once I used LoRa, I got a very good accuracy when it comes to digit 9, but I got around 1061 errors overall. So when I reparameterize my entire weight matrix, it's actually forgetting a lot of things which it had already learned.
Right. Right. So see, this is again, to answer your question, if you want your final model to you know, perform multiple different tasks, then obviously you will have the data set prepared in a way such that the data set can correspond to multiple different tasks, right? On which you will be fine tuning. Obviously, this is also LoRa. You are applying LoRa here. You will be applying LoRa there as well. When you deal with large language models or generative models, there also, let us say you are applying LoRa, and you are fine tuning your pre-trained language model on your custom dataset that contains data instances from multiple different tasks, which are your target, right?
Yes, sir.
If my understanding is correct, that is what you need, right?
Sir, for example, say a language model is first pre-trained on, say, for a task for key phrase extraction, and then I do this LoRa for summarization task. So what happens is the key phrase extraction, the weights that are learned through the key phrase extraction training is actually gone there, correct? No, we have the
It
LoRa
won't
which
be,
is,
it won't be
uh,
gone. It won't be gone. So that is the trick. So the moment you set this enabled equal to false, you will get back your original results on your key phrase extraction you know, data set.
Right,
The
sir. So
moment,
if I enable LoRa, the thing is, I want to do both. I want to do key phrase extraction as well as summarization with the same language model.
right, then you simply don't update. I mean, this calculation, this B cross A matrix is getting added to the W matrix at the very end, right? You
Yes, sir.
don't do that addition. If you simply, avoid doing that addition, then you will get back your original results. This is a very simple, trick. So you can have your base model intact. That's the beauty of LoRa. The base model is not changing. Every time you do not have to upload a new model the moment your end task changes. So let us say you want your model to perform decently on the key phrase extraction task. Okay. Then
Yes.
you don't upload or don't add the updated LoRa parameters. Don't add them. You have trained it. You keep it saved. But when you're at the inference stage, then you do the inference on the key phrase extraction dataset with your original model. When you want to do the inference on your summarization dataset, then you simply add these tuned LoRa parameters and then you perform your inference.
Yes, sir. So that is the case with if I have two tasks, then I train it, then I add or don't add the LoRa parameters so that I do those two tasks simultaneously. But what about if I have one more task, say named entity recognition?
Yeah, see, now large language models are usually pre-trained on a lot of different tasks. Okay, so you already have a decent performance on various different NLP tasks. For example, named entity recognition or key phrase extraction or summarization. Okay, now let us say you have a very specific requirement or maybe a different domain where you want to apply your model to, and you are seeing that the out of the box results or the zero shot results on your domain specific data or your specialized data is not good enough. So then you will have to plan train your model on that specific data set. Now similarly, if you have multiple different tasks, right, like you are saying, you have multiple different tasks. Let us say your large language model was pre-trained on 1,000 different tasks. Now you have 3 new tasks, and you know very well that the original model was not trained on any of these 3 tasks, right? If is this scenario fine?
Yes, sir.
Okay, so now what you will do is you will train one version of the model on dataset 1, which is for task 1. Only the LoRa parameters. That is the beauty. The base model remains intact. You don't have to do anything with the base model. That is anyway frozen. The base large language model. Okay. Now you train one more version with LoRa for task 2 dataset 2. You train one more version with LoRa with task 3 dataset 3. Only the LoRa parameters, only those 6,000. So if I just show you here, if you see this these parameters, only these 6,000 parameters are getting updated.
Yes, sir.
Okay, for different tasks, for different scenarios, right? But the base model, which is the huge model, 2 million parameters, that is still remaining intact. That is not going anywhere. So during production, you say you load your base model only once. Okay, you load your base model only once. You're not going to take out your base model from the memory every time you have a new task. You load your base model only once. Now during inference, you know on which task or which task, I mean, yeah, on which task you are going to infer your results. So accordingly, you can select the LoRa parameters, the fine-tuned LoRa parameters of that task, and you append them to the original weight matrices, and the magic will happen. So
Wonderful.
then you will have good enough results for your task 1. Then you subtract these LoRa parameters, add the LoRa parameters of task 2, do your inference on task 2. You will have better results. Again, you subtract the LoRa parameters and add the LoRa parameters of task 3. Are you getting my point?
Yes, sir. So
The
it's
base
kind
model
of
is
plug
still
and
same.
play so that as the task changes, you just plug different.
Exactly, just plug and play. Just plug and play.
Yes, sir. Thank you,
You
sir.
plug out your unnecessary parameters, plug in your required parameters, and that's it. Your base model remains intact and remains saved or stored in your memory only once. You're not doing anything with your base model.
Yes, sir. Thank you, sir.
Okay. Okay. Fine. So any other question?
Yes, sir.
Yeah.
Sir, you mentioned that we can use LoRa on multiple layers or all layers.
Hmm.
So how do we decide which will give better performance? Generally, do you using LoRa on all layers will give better performance?
Usually, I mean, the original implementation of LoRa and the authors had actually implemented the LoRa on every layer. Okay, because anyway you are seeing that the original matrices, the original weight, I mean the weight vectors, they are frozen anyway, so they are not getting updated. So and now there are 96 different layers in your large language model. For example, GPT, there are 96 layers, 128 layers, many layers. Now, if you apply your LoRa to only one or two layers, obviously you are not going to get good enough performance, right? So usually LoRa is implemented on each of the layer, but at every layer. So like the Q, K, and the V matrices, the query, the key, and the value matrix of the transformer, just think like that. Then you can always decide like for which matrix you want the LoRa updates. So usually in many of the implementations, LoRa updates are only applied on the key and the value, sorry, the query and the value probably. I'm just forgetting, just a moment. Just let me see once. Um, These things again matter from one model to another model. So for example, here you can see that it is being applied only on the query matrix and the value matrix, not on the key matrix. Okay, now these things will vary from model to model, from different size of model to different size of models, and again depending upon your end goal, like how you, these are basically all hyperparameters. Okay, you can test many things because as and when you apply your LoRa parameters to more matrices, obviously more number of parameters are getting added to the model, right? So you can have a sweet spot between this, or the trade-off between these two. Like, okay, I only want to apply my LoRa updates, or I only want to add LoRa parameters only for the Q matrix and the V matrix, but I do not want to add any LoRa parameters for the K matrix. And let us see what how the results are showing up. And these are some standard implementation, standard ways of doing things which authors have played around with and they have shown in the paper. But again, here you can decide. But usually LoRa, if you are only updating a large language model using LoRa, then you apply LoRa at every layer. But at each layer, you can play around with which matrix you want to apply LoRa on.
Okay, sir. Are there any comparative study of like only applying to like 50 LoRa to 50% of the layers versus all layers, like something like that?
Uh, I'm not aware of any such comparison, at least in the original LoRa paper. Just a moment. How do I move to? Oh, okay. This bar is coming here. I'm not able to do anything. Okay, just let me show one thing. Now, if you look at the LoRa paper, then there is one comparison which I can show you. Like if they are applying it on different matrices, then what happens? Just a moment. See, here you can see that, I mean, different size of models, these are what? Yeah, these are the number of trainable parameters. Okay, and these are two different data sets on which the model has been tested upon. Now you can see that they are using ranks for different metrics. So somewhere they are using for all the matrices, the query, the key, the value, the output. All these matrices are being fine-tuned using LoRa, and then you can see the performance comparison of all these models. But again, these are not different layers. They are applying the same configuration to all the layers. This is what they have shown in the original paper. But I take your question, and if I get hold of any such comparison, I will share with you.
Okay, sir. Thank you, sir.
Okay, and I will update on the same. So okay, now you have a copy of my this thing notebook, but anyway, I will share with Professor Mayank, and maybe he can share.
Yes, sir.
Okay, all right. All right. I'm really happy to take more questions, but in the interest of time, let us just complete this thing, because Q LoRa is a very beautiful technique just on top of LoRa. So I will just complete this, and then I will go back to taking questions. Okay, fine. So what Q LoRa says that, okay, in LoRa, during the inference time, you are not getting any advantage. You are only getting the advantage during the training time, right? You are only updating some number of parameters, the additional LoRa parameters which were getting added because of the LoRa implementation. However, the original weight matrices, the original weight vectors are all frozen, right? They are you are not touching any of the original model parameters. However, in the model, you will have to load the entire model, all the model weights, right? You may not update. You are calculating the gradients for some amount of parameters, but your model needs to be there in the GPU RAM, right? In order for the computations to take place. And that itself is an overhead, because with the sizes of models that are currently getting published, they are huge. 7 billion models, 16 billion models, GPT is 175 billion models. Now, obviously, for an average user, if you want to upload your model with the original weights in their original precision, then it will be a huge headache. Now, do we need original precision? By original precision, I mean the precision with which the values in those weight matrices are saved. Usually those are 32-bit precision values, okay, FP32. So now what this Q LoRa paper says, that since anyway majority of the original weight vectors or the original tensors or the original weight values are anyway frozen, they are not getting updated anyway, okay, only some number of parameters are going to be updated. So let us load the original weights with a lower precision. Rather than a 32-bit precision, let us load it in a 4-bit precision. Obviously, you can see that there is some accuracy loss, right? Now, only for the computation, for those parameters which are going to be computed, on which some computation is going to be performed, just load them in their original precision, or maybe a 16-bit precision, but load the other parameters in a 4-bit precision. So immediately you can see that there is a huge compression from 32 to 8 to 4 or 8-bit, let us say, right? So there is a 16 times or maybe a 4 times compression that you immediately can enjoy, and then you can upload the model more efficiently in your small GPU. So let us say 16 GB GPU only you have. Okay, that is the beauty of Q LoRa. And then Q LoRa introduces 3 different techniques, which let us say, if I can explain them to you, but let us go ahead with this. Okay, gradually I will say the how to. So this is called the quantization loss. Now, I mean, when you are basically saving the original weights with a lower precision value, then you are quantizing it. You are quantizing the original values to a fixed number of bins, okay, and then during the computation you dequantize it. Okay, so this is how the process goes on. Now there is an accuracy loss in between. Now how to reduce that loss? For that, the Q LoRa authors have introduced multiple techniques. Okay, so let us see if I can explain them later, but let us go with the implementation first and complete this. So yeah, I mean, obviously we need some libraries. The bits and bytes is going to be the key, because with bits and bytes library, you will be implementing the Q LoRa part. Okay, you need the PEFT library, because now you no longer, I mean, above we saw the implementation of LoRa from scratch. Now later on, when you are working, actually, you will no longer be needed to implement your own LoRa, right? These things are already implemented in the PEFT library. You can directly use it. Transformers are fine. TRL is basically for supervised fine tuning. You have your SFT trainers and trainer objects. For that, you need this TRL. library. Okay, so here we are going to perform this process on a dialog summarization dataset. Let us say this is our end task, fine, and we are going to play around with llama 2 model, which is pretty huge. I mean 7 billion model. All right. Okay, now this is how the datasets are being loaded, so which is fine. It contains dialog and a summary. These are our two columns on which we care about. So dialog is our input, summary is the outputs. We are summarizing the dialogues. That is the dataset, right? Okay. For simplicity, we are only considering the first 20 samples from the test set. Again, you can, this is just for the demonstration purpose, you can play around with the entire dataset. You are loading it. Okay, here we are converting the dataset to a Panda data frame. I deliberately kept these things because it helps in better visualization, and you can easily implement some prompt tuning or instruction tuning on this. Add the instructions in a more viewable way. So okay, so this is your train data frame. You can see there is this dialog, there is a summary. Okay, now we are preparing the dataset. So Llama has a specific way in which the prompts are written. I mean, Llama during its pre-training phase, right? Its pre-training dataset has a particular way of designing the prompts, right? The training prompts. So this is how it goes. First, you have your instruction, right? And every model, by the way, every model during its pre-training has its own specific type in which the instructions are provided to it during pre-training. So during fine-tuning, whatever be our end task, maybe our end task is completely different. But if we follow the same prompting technique at least, okay, then we can be at least rest assured that, okay, the model has seen these kinds of prompts before, just that the prompt is changing, the task is changing, but the template is not changing. So if you are using the same template, then it helps the model to at least not get confused. So that's why I'm setting up the prompt in this manner. So first you have your instruction, then you have your input, which is coming from this dialog, right? Input queue. So instruction, this is the keyword, then your instruction comes, write a concise summary of the following below text and all that. Then your input prompt comes, and then your actual input comes, which is your entire dialog, then the prompt response, and then your actual output. Now during training time, we will have this output because we are going to, we have to calculate the losses. So we know what the outputs are because we are doing supervised fine tuning, although in a parameter efficient way. And during the test set, you can see that this output is not appended. All right. So hopefully this is clear, like how to prepare the train data and how to prepare the test data. Fine. Okay. Now, once you do this, then you can see that the dialog and the summary columns are unchanged, and this text now contains. So this text, everything that has been now prepared, that goes into a separate column called text. Okay. So this text column has now been filled up, and we will only care about this text column while we are doing the fine tuning process, because this contains everything. This contains the instruction, it contains the input, it contains the desired output, everything is there. And by the way, we are preparing the data in this manner because Llama is a decoder only model, right? This is not an encoder decoder model. So there will be encoder decoder models as well, like T5 or FLAN T5. For that, we do not prepare the data in this manner. We only give the instruction and the input to the encoder side, and the output is sent to the decoder end, okay, during the loss calculation. So the way you prepare your data also changes depending upon the model. Okay, so because this is a decoder only model, there is no separate encoder as such. So the entire thing, the instruction, the input, and the output, entire thing has to be sent to the decoder. That's why all the three things have been appended in this manner for preparing the training data set. Okay, hopefully this thing is clear. All right. So now this is how this is the input. This is how an input goes. So this is just printing one of the first entire prompt that you are sending to the model. So first you have the instruction. Your instruction is there. Then you have the input, which is your entire dialogue. Hi, Mr. Smith. I'm Dr. Hawkins and all that. Okay, two persons are speaking, communicating with each other, and finally you have the response, which is a summary of the entire conversation. So this is how your entire data instance look. The by data instance, I mean everything, the input, the instruction, the desired output, everything. All right. Similarly, you can see that this is how your test data frame looks, and this is how your first data instance looks. Very similar, just that the output is not there. Okay. After the response, now you want the model to generate the output. All right. Okay. So fine. Sorry. Okay, so fine. So now what we are doing is we are, somehow my mouse is not working. Anyway, I will go ahead. So now what we are doing is we are converting the dataset from pandas to the datasets format. Okay, using which Torch, would perform the processing. So the dataset now looks like this. Okay, same thing, just the text column now has been added. Okay, so now you are here. So basically you are uploading, you are downloading the Llama 2 7 billion model in the sharded format, so that you can, load it more efficiently. And here, then the quantization config is the main part of this particular, this QLoRa part, right? So you are directing that you load the model in 4 bits. You are setting it to true. Now, this double quantization is one of the tricks which this QLoRa authors have come up with, which helps in reducing the quantization error. Okay, so you're also setting it to true. Now, the first trick that the QLoRa authors, suggested or kind of discovered is this normalized, precision 4 data type. So this is a new data type that has been, given away by the authors of QLoRa. Okay, so you're using, so what this does is basically it, first of all, it normalizes all your weights with a mean of 0 and a variance of 1. Okay, and then it applies the quantization. Okay, and they have empirically shown that if the weights are centralized around 0, so if the weights are normalized around 0, and then you apply the quantization, then it helps in achieving better results. And also, not all the bins are of the same size. That is one more trick, which is also provided by the QLoRa authors. Not all the bins. So during quantization, you have some fixed bins, right? Into which you are mapping any number that you get in your weight matrix. You are mapping any of those numbers into one of these fixed bins. That is what quantization means. But usually, all the bins will have the same amount of, same size, right? Now, what the QLoRa authors have shown that once you normalize all the weights, then majority of the weights are going to come in the middle. And as you taper down on the side, then the number of weights are going to be lesser. So towards the end of that tail, the bins are of larger width. And when you come towards the center, then the bins are of shorter width, just to ensure that two different values are not, if they are very near to each other on the number line, then they are not quantized to the same bin. Okay, so for ensuring this particular thing, they have basically suggested different sized bins for doing the quantization, and this is one of their major reasons for performance improvement. And accordingly, they scale the weight, their bins, um, with respect to the normalized weight. So there are some more details which you can go through the paper and read. In the interest of time, I will go ahead. But this is how you are basically defining your quantization config. Okay, so load in 4-bit, you load all the remaining parameters in 4-bit, you set it to true, you apply double quantization in order to reduce the quantization loss, and then you set the quant type to normalized 0.4. Okay, normalized precision 4. Fine. And during the compute time, you can see here, during the compute time, you set the precision to B float 16. Okay, brain float 16. Okay, so there's a float 16 computation that will be happening. All the other bits will be loaded in bit 4. Okay, okay, so fine. Then you load your model, you apply this quantization config, this BNB config which we have set here, and that's it. Your device map equal to auto means that depending upon the scenario, your model can toggle between the GPU and the CPU. So internally, Torch will take care of all these things. So that's why you can set the device map equal to auto. Now your model will be downloaded, and the tokenizer will be loaded. All these are fine. And when you print your model, then you can see that this is loaded in linear 4-bit. This K matrix is also loaded in linear 4-bit, right? And this is going on for all the 32 layers that this model has. All right. So this is how the things become better if you load your model using QLoRa. Okay, the majority of the weights are going to be loaded in 4 bits. Fine. So now, with the original model out of the box, let us just check the zero shot inference. So if this is my input, right? If this is my input, this is the first instance from the test data. If this is my input, and if I apply, model.generate, now I have not trained my model. This is the off-the-shelf Llama 2 7 billion model loaded in 4 bits. If I do, simply take an output of this data instance, then this is how the output looks. Summary of the above text: the company has decided to ban instant messenger from its offices because they waste too much time and all this. Okay, this has been generated by the model, and this was my input. This was my original input. Okay, fine. So now let us go into the training phase. So now, till now you have not yet applied LoRa. Till now you have just uploaded the model using the QLoRa facility, okay, so that the model can be loaded in a better fashion and the computations can happen in proper precision. Now gradually we come into the PEFT. Okay, so from PEFT, first we prepare the model for KB training. Again, this is also for some optimizations. This is still not LoRa. Okay, there's again for some optimization, so that the models are, the models are trained in an optimized way. The model weights are loaded in an optimized way and all that. Okay, even without this command, the model can still run. This is just to make the training more stable. Okay, now we define a function to print the trainable parameters. Now comes the beauty of PEFT. Okay, so you define your LoRa alpha. Yes, you define your LoRa alpha. So now all these parameters which you are defining, while preparing the class, while defining the class, now everything comes out of the box from this PEFT library. This in future you will be using this only, right? So you set LoRa alpha to 16 here. I have set LoRa rank equal to 2. You can see that the rank is really small. I have deliberately kept it so that I can show you one complete iteration of the epoch. That's why you can set it to 8 maybe. So that way your scaling factor will become LoRa alpha by LoRa rank, which will be 2. Okay, if you set it to 8, I have set it to 2. And dropout, you know what dropout means. And then you define your LoRa config, right? That this is your LoRa alpha, this is your LoRa dropout, which are your target modules in which you want to create, you want to add your LoRa computations. So the Q matrix and the V matrix, you define your rank. This is the most important hyperparameter, and bias is none, which is fine. And the task type is causal LM. Why? Because this is a decoder type, decoder only model, a generative model, and is a causal language model. So that's why the task type is causal LM. Again, there will be different types. For example, if you try LoRa with FLAN T5 model or T5 model, which is encoder decoder model, then the task type will become sequence to sequence. That will be the phrase. So depending upon your model that you are training with, just make sure that you are defining the task type properly. Okay, and this is where you load your model using PEFT, using LoRa. This was your original model here. This is your original model, but you apply your original model with the LoRa configuration, and then you reload the model. So after you reload the model, you can see that what are the number of training parameters? Only this much, and all parameters is this much. So you can see that the trainable percentage is only 0.03%. Can you imagine such a drop? Only 0.03% of the model parameters are going to be fine-tuned, and you will get good enough results. That is the beauty with LoRa. So here I have combined two things. One is uploading the original model using QLoRa or in a quantized format, and then applying your LoRa. Okay, two things are combined. You can do away with one of the things. For example, you can just upload the model using your QLoRa configuration. Do not apply your LoRa. Do the full fine tuning. If you have enough GPU, computations, GPU infrastructure, you can do that. Also, if you have enough GPU, no need to load your model using QLoRa. Just load your model as it is, and then applying your LoRa. Okay, that also you can do. It will be parameter efficient, but the model will not be saved in an efficient manner. Stored in an efficient manner. Okay, so you can play around with one of the two things. But again, I've just punched in both the things together so that this becomes the most optimized way of doing things. Fine. So then you define your training arguments. You can understand output directory is fine. Per device train batch means for every device, what will be the size of the training batch? So I've set it to 1, just that it fits into one GPU, and I can show you. Gradient accumulation steps is a very important parameter. I'm not sure whether am I just repeating them. You already know them. So if you already know them, just any one of you can just tell me that okay, we know them. You can just skip this part. Um, do you already know these things? Okay, I will take that as a no. Fair enough. So gradient accumulation steps means, see, per device train batch size is 1. That means after every batch, your batch size is 1. So in every batch, only one data instance is going in, right? So this way, if you are performing batch gradient descent, right, the batch gradient descent function, then eventually for every instance, your gradients will be backpropagated, and that will be too heavy. Okay, so that's why there is this parameter called gradient accumulation steps. So you can keep on calculating the gradients, but you accumulate your gradients. Do not do backpropagation at least till 4 batches have been read. This is what it means. Okay, so for computing the loss, you send one instance at a time, but you are not going to backpropagate at least till the point you have calculated the gradients for 4 different data instances. So this is a very helpful parameter that you will be coming across in your trainings tomorrow. And then you set up the optimizer. Again, paged Adam W 8-bit. This paged optimizer is one more technique which the Kueller authors have proposed. I'm not going into the details. You can check it in the paper. Then the learning rate is fine. LR scheduler type is fine. Logging steps means after how many steps you are going to log. Max steps, you can set it to 10. Obviously, this is a very crude way of showing you the training. You obviously, with max steps 10, your model won't be trained sufficiently. So we'll have to train it for more number of epochs. You can play around with these things. Okay. And then with all these arguments defined, now you can define your trainer. Okay. You define your trainer and you can see that the dataset text field is the text column which we prepared. All right, and you send your LoRa config, you send your training dataset, you send your model, you send your training arguments. All these things are sent, and your trainer is ready in order to train the model. So fine, then you train it. Okay, this is one more trick. I mean, upcasting the layered norms in float 32 for more stable training. You can even complete the training without this particular cell. Then you train the model. So since I had requested the model to just log for every step and only train it for maximum 10 steps. So that's why you can see that the model has only been trained for only 10 steps, and there is not much training loss difference. From 1.9 it has just reduced to 1.6, which is fine. I mean, this is just a 7 billion model has just been fine-tuned for 10 steps, which is not good. So just to show you that the overall processing is fine, and once the model has been trained, then you can save it. And during the inference time, again, you define the LoRa config. This is important. And from the saved output, you define your LoRa config. You do not have to go back to the original configuration, define every parameter like LoRa dropout is this much, LoRa rank is this much, and then you will have to define the LoRa config. Just from the saved things, you can define your LoRa config using this call, and you get back your model. Now, because this is a inference time, you can see that the trainable parameters are 0. Okay, no parameters are getting trained now. Now you are into the inference stage. So your input is supposed to pass through all the model parameters. And this is why I told any advantage during the inference time. During the inference time, your input is going to pass through all the model parameters. So that's why your entire model needs to be in the GPU. The performance improvement is only during the training phase. Obviously, if your all if your parameters, all these parameters, if they are loaded in 4-bit, then obviously it helps in further memory storage reduction. So again, you set your inputs, you get your outputs using model.generate function, and you print it. So again, for the same instruction, same input, you will see that this is the summary. Again, you can verify that this is the same summary which was given by the model before tuning. Why? Because the model has not been sufficiently trained. Now, when you train it sufficiently, then obviously this summary will improve. This will change. This will update for the better. So yeah, I mean, this is more or less what I had for today's hands-on session. If you have any further questions, I can take them. So this is how you use the PEFT library, use the transformers library, use the bits and bytes library, and you train your large language models. Here I have shown 7 billion Llama 2 model. Okay, you train your large language models using these techniques or using these libraries very efficiently. Okay, and you can play around with just by trying LoRa, just by trying QLoRa, a mix up of two, which I've already shown. Change the batch size, change the gradient accumulation steps. You can play around with all these things. Obviously, you can change the rank as well. For LoRa, that is the most important thing. But usually in the papers, they have shown that beyond a certain rank, there is no much improvement. Okay, so beyond the rank of 8, they have shown that from rank 8 to rank 256, usually you do not get much improvement. This is a peculiar result, but that is what has been shown. And why this phenomenon works is because the pre-trained large language model was pre-trained on a lot of different tasks. But when you are pinpointing on a particular task, then the intrinsic dimension of the weight matrices reduces. Okay, the intrinsic dimension reduces. The actual important information for that particular end task can be well accommodated within a very small rank. And this is why you don't see much improvement when you increase your rank beyond a certain particular value. So that is more or less about LoRa and QLoRa. So yeah, and these are some additional resources. Obviously, Professor Modi has prepared a fantastic tutorial. You can see other techniques like soft tuning, soft prompting, prompt p tuning, and all those things in this tutorial. Although nowadays, whenever in the practical settings, nowadays people are going ahead with LoRa, QLoRa. There are different variants of LoRa, like Ada LoRa. I think you have already come across that. Then there are more efficient methods like PISA, Galore. There are a lot of different techniques, lot of different siblings of LoRa. So once LoRa has come into the market, now people are starting off with LoRa and then going into more recent techniques. But still, I mean, the older techniques you can, obviously, browse through this tutorial. And I have also given the links of the original papers as well as some YouTube videos, which you can definitely refer to. It will help you in understanding, which I just explained. So yeah, with that, I come to the end of this session. So I'm ready for questions.
Hello.
Yeah.
So given QLoRa applied on dialogue summarization,
Yes.
Is there any, I mean, if the size of the documents are increased, like if you're performing QLoRa on long document, is there a effect on such documentation size and the evaluation metric for QLoRa or LoRa? I mean, if it's dialogue, so it's small, the input. If we take a document, imagine 100 sentences and there are multiple documents to do so. So does other evaluation metric like coherence has a problem in such long documents?
Okay, so let me just rephrase your question. So I'm just telling you certain points. Just verify whether I'm in the right track. You are talking about a scenario where during the inference time you have longer documents.
Yes,
Is
sir.
that correct?
Yes.
Okay, but you have trained your model on this dialog summarization dataset. Is that correct?
Yeah.
Okay, so that means you are again going back to zero shot inference kind of a thing, because the model was trained on something else and you want to test your model on something else. Now, if your inputs are long, now Llama 2 probably has 4096 is the input length, or what is the maximum input length of Llama 2? I need to check. Either it is 8192, 4092, something around that characters. Okay. Now, if let us say your input is longer than that, then if you do not apply techniques or tricks to, now the tricks, by tricks I mean some attention mechanisms are there by which you can use the same model, but you can read a longer input than its actual limit, the context limit that the model has. Let us say the model can at max read up to 4096 characters, but your document is 8192 characters, so double the size. Now if you simply take the model and you apply your input, then your model and their input will be truncated after 4096 characters. That's what happens. So you will lose the context of the next 4096 characters that your input has. Okay. Now in those cases, some how to extend uh, the context length of an already pre-trained model. There are many papers on that. So some tricks have to be applied in order to read such longer context. That is point one. Now let us say that your input is still up to 4096 characters, but you have fine-tuned your model on a data set where your inputs are maybe around only 512 characters. Okay. I think you are referring to this particular scenario where your fine-tuning data set is very small. I mean, the context length of the fine-tuning data set is small, but during the inference, you are getting longer inputs, right?
Yes.
Okay. So in this particular context, then you do not need to apply any trick to increase the context length because your input is well inside the context length, just that it has not seen that long input during the training phase. I mean, during the fine-tuning phase. Now, probably it has seen such kind of longer inputs during the pre-training phase. If it has seen such longer inputs, then it will try to calculate the information from the entire context, and it will try to give you a result. But the moment it has been fine-tuned on something which is very different from what it is seeing now, obviously there will be some drop in performance. If you can have such a training data set, or at least if you can give it some in context learning kind of a few short prompts, or not zero short, but at least some examples like in context learning, then it will be better equipped with understanding, okay, like how to read the entire context of this much length and how to produce the output. Because the moment you are directing the model that, okay, I mean, you have been pre-trained on a lot of different tasks, I do not care about that, I have a very specific end task, and you are fine-tuning on that end task. Now suddenly during the inference time you are again supplying something very different, then obviously the model is supposed to get confused. Okay. And it will not probably give you the desired outputs. So in order to ensure that at least you have such kind of a data set, I mean, so that the distribution of the lengths is almost like equal during the training. I mean, by training, I mean the fine tuning phase and the inference phase. If you cannot ensure that, then it's better that you do not even, train or fine tune your model on such a different data set. Now, if you say that, no, the dialogues, I mean, the long inputs also consist of dialogues only. It's just that the dialogue length is longer. Then you can, just rely on its pre-trained knowledge and the fine-tuned knowledge on how to process dialogues, and then you can rely on these two information and expect the model to perform good. But if you are asking about some performance drops in some of the coherence metrics, I think it will be the case. I think it will be the case because the model has been pre-trained. It has some pre-trained world knowledge, that is okay. Maybe it has seen longer contexts, so that reading longer contexts is coming from its pre-training knowledge. Now, during the fine-tuning stage, it has seen dialogues. So the context of a dialogue, how a dialogue looks like, all that information it is now learning during the fine-tuning stage. But in the fine-tuning stage, it is only reading smaller contexts, smaller dialogues. Okay, but at least it is reading dialogues. So the information about dialogues is coming during the fine-tuning stage. Now during the inference stage, if you are mixing up the two, that you are suddenly you are sending longer dialogues, then I think that is the only way out, that the model has to rely on its fine-tuned knowledge and pre-trained knowledge, combine them, and then produce the output. So, but again, the coherence metrics that will at least will take a hit, and that is my guess, because the fine-tuning data set or the fine-tuning characteristics are not exactly as the inference data characteristics.
Yes, sir. Thank you.
Hello, sir.
Yeah.
So I had a doubt in Q LoRa. So when we calculated the LoRa parameters with a quantized model, got some parameters, but for at the time of inferencing, can I use these parameters along with the original model? Would that improve accuracy, or should that not be done?
Parameters with the original model in the sense?
Like which was not quantized.
Okay, which was not quantized. Okay, so you are saying that during the inference stage, you do not want to apply do not want to load the model in 4 bits, right?
Like the full original model, which was not quantized, and we quantize it only during the training phase, but not, but when we like infer, then at that time, maybe we load the original model along with these parameters, LoRa parameters.
Yeah, I think I got your question. I'm just rephrasing it. Just let me know if I'm going wrong. So you are saying that during the training stage, you are loading the model in 4 bits, not in the original precision. You are loading the model using QLoRa. Then you are applying LoRa, right? And you are combining both the concepts. So QLoRa and LoRa, when they are combined, and you efficiently train the model where the model has also been stored efficiently. So not only the training is efficient, the storing is also efficient. Now your training is complete, right? So now you are saying that, okay, my training is complete. Now I want to get back to my original model with the original precision of the parameters, right? Is that your question?
Yes, that is my question.
Okay. So yes, I think when you are, see, first of all, you can see that when I get back my model here, right? After the model has been saved and I load the model again for inference, then you can see that the trainable parameters are 0. So I'm again playing with the original parameters. So at least one point is clear, that here during the inference stage, LoRa does not play any part. Okay, the inputs are going to pass through the original model parameters, and then your outputs are going to be generated, right? So LoRa is not playing any part during the inference stage. Okay, now whether these weights are in 32-bit precision or in 4-bit precision, that is your question, right? Like in what precision they have been loaded during the inference stage.
Yes.
So I believe that this probably you can, I have not played around with, so I do not have a definite answer. But since this is a configuration, okay, I think you can change the configuration here and reload the model, reload the same model, the fine-tuned model, okay, where you can set it to false. You can try this. You can try this, because the moment the double quantization happens, then because automatically this quantization loss is being taken care of when you set this double quantization to true. Okay, and anyway, during the computation stage, because during the inference stage, some computations, some computations will be flowing through the entire model, right? So during the computation stage, it will still be calculated using precision 16. So it is not precision 4. So uh, I don't assume that you will lose much during the inference stage. At least, otherwise, the paper would have told in that manner. But still, this is something which I also need to check. I'm not exactly sure, but I think that during the inference stage, this Q LoRa part does not. LoRa definitely does not play any part, but this Q LoRa part also does not play a part, because anyway the computations are going to happen in float 16 precision. So you won't lose, much precision or accuracy in the outputs.
Okay, all right, sir. And just one more question. So we choose the rank. Why do we generally choose it in the power of 2 for LoRa? Is there a particular reason, or is it's just a convention or something?
As far as I know, it's just a convention, but probably there is a reason as well. I'm just thinking, let's see. Because usually if you see the dimensions of the weight matrices also, usually they are in the power of 2, like 64, 32 and all that. Let me get back to you. I'm not able to think of any particular reason, but usually that has been the standard. I have seen that the ranks are in powers of 2. So 2, 4, 6, 8. I mean, these are not 6, 2, 4, 8. These are some common ranks that at least I have experimented upon. And yeah, I just simply followed the trend. I did not think too much about it. But yeah, that's a good question. I mean, I will get back to you with a proper reason.
Okay, sir. Thank you, sir.
Thank you.
Okay, I think there are no more questions. Okay, thank you, Rajdeep, for this excellent session. I think it was quite interactive compared to our earlier. Okay, you have.
Okay.
Rajdeep, there is one question.
Yeah, I can see the hand.
Hi, Rajdeep. This is Ashutosh. So just one clarification question, more on the implementation side.
Yes.
So if I have like LoRa weights trained for different tasks, right?
Yes.
And now I don't remember exactly, but I read somewhere in one of those papers. In some paper I read that what people are trying to do is they are taking the sum of all these update weight matrices,
Yes.
and then
Okay.
you are able to do LoRa over multiple tasks
Multiple
in
tasks.
a single batch. So is that the way usually people combine multiple tasks in LoRa?
Thank you, Professor Modi, for that question. So practically speaking, I have not implemented that kind of a setting yet, because there are maybe 2 or 3 tasks and we have specific data sets on which we can train, and we are inferring it separately. So I have not combined the weights and then tried to infer. But yes, if the LoRa parameters of, the fine-tuned LoRa parameters of 3 different tasks are summed up together and then added to the original weight matrices, then logically the model should perform better than the pre-trained model on these 3 different tasks. But if we check their individual performance, like only the LoRa parameters of task 1 and I do the inference, versus I combine all the 3 different LoRa parameters and then I infer on task 1. I'm not sure whether there will be any in the second case.
Okay.
So yeah, that is a doable thing, I would say. I have
Okay.
not come across that a scenario, but yeah, this can very well be tried out. Definitely be tried out.
Okay. Okay. Thanks. Okay.